Hello everyone, welcome back to the course on materials informatics. In today's lecture we will talk about density function theory or DFT. So just as a recap of what we did in the last lecture, so we discussed graph neural networks which are a natural way to model materials, so both molecules as well as crystal structures. We also looked at some of the challenges that graphs have in terms of modeling structures. So we looked at the node order invariance issue, we looked at variability issue, and for crystal structures translational invariance issue as well. There are also solutions that are available, and we looked at how they are implemented in graph networks, and we also looked at some of the hyperparameters associated with graph networks, right. So graph networks sort of represent the end of the first sort of 1/3 of the course or the first module of the course, but we will revisit graph networks in the final module of the course more towards the advanced topics. But for now in the second module of the course we will do more or we look at physics based modeling of materials, or how do we calculate or estimate properties of different materials using principles that come from fundamental physics, from the basics of it. So in this lecture we will start looking at the basics of density function theory or DFT, which is a very common computational framework that is used for modeling materials. From this lecture onwards we will be deviating significantly from the book by Aurélien Geron. So I will be using schematics from various other sources which I will cite on their respective slides. Okay. So what is one simple way of looking at these physics based computations or simulations, right. So in the first module of the course we looked at different machine learning sort of algorithms or machine learning tools, so ranging from simple classical models to more advanced graph based models, right. You can think of them as engines of your car, right. So these machine learning models basically take in sort of any kind of data and then they create an output or predict an output. So that is similar to how an engine works. So engine takes in fuel and then does actually work, so it takes you from point A to point B, right. So machine learning tools or techniques can be considered as engines, and one of the critical inputs for any engine to work is actually the fuel, right. So where is the fuel coming in from for a given engine, or in our case where is the data coming in from for these machine learning models to actually learn from. So almost always you will see that when it comes to modeling materials and to an extent also in chemistry, so modeling molecules and so on, the data is almost always going to come from your calculations, right, calculations and simulations which are based on physics based principles. So we can sort of generally call them as physics based modeling or physics based simulations or calculations, but it is these computational data or calculated data that is going to give us the fuel for building our machine learning models. So it is very important to understand where the fuel comes from, and B, what is the quality of the fuel, right. So when is it that we are guaranteed to get good data when we use these physics based models, and when is it that we do not get good data, right. So in that sense it is very important to understand the physics that goes into generating these forms of computational data. Now in the modern era, or in the very recent past, there have also been efforts around the world to establish what are referred to as autonomous labs. So these labs use robotics to do high throughput experiments and hence generate very systematic experimental data, right. So experimental data or very systematic experimental data can also be used for these machine learning models, but as of today the availability of systematic experimental data is still sparse or fewer compared to the availability of systematic computational data. Because the computational workflows were almost established about 1.5 to 2 decades back. So and the sort of computational engines were set up long back, right. So we have had the time to actually accumulate quite a bit of data, quite a bit of computed data. So that is why you would see that most of the machine learning models that have been developed and being deployed in the modern era have almost entirely relied on computational data and very few experimental data that usually comes in for validation or some kind of hyperparameter tuning, right. So since computational data forms the fuel for our machine learning model engines, it is very important to understand this fuel as well. Okay. And what is the main sort of main focus behind these physics based models when it comes to predicting material properties. So if you look at most of these physics based models, they sort of worry about where electrons are located in a given material, or in a given molecule. And why are electrons important, right? So when it comes to the study of materials or in the study of molecules, electrons basically influence bonding, right? So they sort of dictate whether you get a metallic bonding, whether you get an ionic bonding or a covalent bonding. So in metallic bonding you have sort of almost even distribution of electrons across space. So all the electrons are shared by all the atoms in a given structure. In an ionic bonding there is distinct electron donation that happens, right, and in covalent bonding there is directional sharing of electrons, right. So there are distinct directions along which electrons are shared, and the other directions there are no electrons, right. So electrons basically dictate bonding, and if you think one level above bonding, so electrons dictate bonding, and bonding in turn dictates properties of a given material. Right. So if you think about a structure with high degree of metallic bonding between the electrons, its electrical resistivity is going to be low, or is going to be an excellent electronic conductor, right. The length of a bond is also determined by the type of bond, right, and if you think about your geometric parameters like your lattice constants, which in turn determines what kind of symmetry or space group your crystal structure is going to occupy, and what kind of crystals it's eventually going to form, right. The bond length actually comes from electrons as well. So electrons basically determine what is the length or what is the distance between two atoms in a given structure. And they also influence what is the typical energies needed for breaking or forming of bonds, right. So in a structure, so if you think about molecular reactions, breaking or forming of bonds is inevitable when you have a chemical reaction. So if you are modeling chemical reactions, then you need to worry about how these bonds are breaking and how new bonds are getting formed, right. In structures you can also think about defect formation. So in defect formation you typically have if it's point defects, for example, you typically have breaking of bonds. In some cases you can also have forming of bonds when you are introducing newer atoms, newer species into different sites in your crystal structure. So bond breaking, bond forming is also very important for defect properties, and defect properties in turn are very important for most applications. So be it semiconducting applications, be it infrastructural applications, be it energy applications and so on, right. And bond breaking or forming is also very important for surfaces. So surfaces are very important when it comes to catalytic applications, right. So how molecules adsorb onto a catalytic surface, whether the catalytic surface itself is stable, what kind of defects that it actually forms on the surface itself, they all contribute to catalytic activity, and hence bond breaking or bond forming plays a crucial role. So you see that electrons influence bonding, and bonding influences very many properties that are practically relevant, right. So it's important for us to capture with accuracy or as accurate as possible where electrons are located in a given material, right. So that's basically the stated objective, right. So need to identify optimal location of electrons for a given set of nuclei, right, in a given material. And this is not straightforward, right. So we will probably need some physical laws, maybe a few approximations as well to do this exercise. So let's look at what are some of the laws and approximations that help us or enable us to do this. And before we go through the approximations or laws, what kind of properties can actually be calculated if you can identify where the electrons are actually located in a given material. One is you could evaluate how the energy of the material itself is varying as a function of changes in volumes, right, and this is directly related to mechanical properties, your elastic constants and so on in a given material. So your elastic properties are all dependent on the curvature of your energy versus volume or energy versus some kind of lattice constant curve, right. So these curves are fairly important. So once you identify or calculate these curves, you can straightforwardly calculate elastic properties or mechanical properties of a given material. You can also estimate electronic properties. So this is an example of a silicon band structure, right? And band structures are extremely important when it comes to any semiconducting application. So think of manufacturing transistors, chips, sensors, and so on. These electronic properties are crucial, right? We can also think about some kind of phonon properties or sort of vibrational thermal properties. So how is the specific heat of a given material changing as a function of temperature, right? And these are fairly important to know to understand the stability of a material as a function of temperature. We can also think about stability of a material at with respect to other materials itself, right? So let's say you have one phase here AX which is competing with a bunch of other phases in your chemical space. How stable is this AX compound or phase compared to other phases, right? So this is something that we can also estimate. So thermodynamic stability of a given phase, of a given structure or a given molecule can be estimated if you know the sort of optimal locations of electrons. Even more advanced applications. So let's say you are interested in calculating some kind of Pourbaix diagrams, right? So this is potential versus pH diagrams. Pourbaix diagrams are very often used to estimate the tendency of substances to corrode. Right. So these are very important for infrastructural applications. So we can actually theoretically calculate Pourbaix diagrams if we know where electrons are located in a given material. And not just thermodynamic properties, right? So we can also estimate or calculate kinetic properties. So how easy it is for atoms or ions to move in a given structure, how easy it is for molecules to rotate, molecules to form or break bonds in a given structure. These are basically kinetic properties, and these can be estimated as well. If you know the optimal locations of electrons. So typically in most kinetic properties you will have some kind of an activation energy associated with either the motion of atoms, or this can also be a chemical reaction, right? So where you go from reactant to product through some kind of an intermediate state. So in such scenarios we can also estimate what is the sort of energy barrier associated with these types of transitions, which then contribute to kinetic properties. And I have just given a small subset of properties here. So we can also think about magnetic systems, right? So we can think about estimating ferromagnetic to antiferromagnetic transition temperatures, or ferromagnetic to paramagnetic transition temperatures. We can also think about optical properties such as spectra that you can get, absorption spectra, reflective spectra, and so on. We can also think about how easy it is to transport electrons in a given material. Transporting electrons as well as transporting holes, and these play a crucial role when it comes to again semiconductor based applications and also more advanced energy applications such as photovoltaic devices. So you see that if you can identify where electrons are optimally located in a given material, you have access to several different properties of that same material, and once you have access to several different properties, you can now think about which material would be most suitable for a given application. Or in other words, if you have a target property, which material would be close to that target property that you are after, right? So you see that if you can model electrons very well, you can basically predict at the material scale, at the bulk scale, which materials would be good candidates. Okay. So let's now think about how to what sort of physical principles, physical laws and approximations are required to estimate where electrons sit optimally in a given structure or in a given molecule, right? So these set of principles or set of approximations or laws are referred to as first principles, right? So it's also the Latin words are also often used. So ab initio just means first principles, right? Basically first principles are a set of accepted approximations. These generally come out of some fundamental laws in physics, right? So some fundamental laws in physics, some of them are reasonable approximations. So they are approximations that are sort of good enough for most practical situations. Once you use these first principles, it sort of minimizes the total number of inputs that you need to model a given system. So ideally we would only like to have just the type of the atoms and the position of the atoms in a given structure or in a given molecule, right? So if you want to model sodium chloride for example, ideally we should only know the box size, the dimensions of your cube, where sodium is sitting and where chlorine is sitting, that is all, right. So that is basically with the inputs that we are after, right. So the idea is if you use the optimal set or a good amount of approximations, you should be able to take these minimal inputs and still be able to predict where electrons are going to sit. So once you take these minimal inputs, pass them through these approximations and through a computational engine, you try to calculate properties, right. And as I mentioned before, the properties can be either structural, so what kind of crystal structure it forms, what is the bond length, lattice constants and so on, electronic properties, whether it is a metal, semiconductor, insulator and so on, thermodynamic properties, whether it is stable, unstable, what kind of defects it forms and so on, magnetic properties, whether it is a ferromagnetic system, paramagnetic system or other forms of magnetic properties as well. So once you calculate properties, you can now start making predictions, so whether a material is good enough for a given application. Okay, so what is the physics, right? So let us start with that. So the very first set of physics that we need to worry about when it comes to electrons as well as nucleus is electromagnetism, right, and that is because we are dealing with charge systems here. So electrons have a unit atomic charge of electrons have a unit charge of -1, and nuclei or protons have a unit charge of +1 atomic units, right. So whenever we model or we have to model charge systems, we have to worry about Maxwell's equations of electromagnetism, right. So this talks about how electric and magnetic fields are going to vary as you change your charge densities and also with time, right. Usually we do not use all the different Maxwell's equations, we try to have in other sets of approximations that help us use simplified versions of these Maxwell's equations, okay. So but Maxwell's equations are a start, so these are important equations to know when we are modeling charge systems. The second is we also have to worry about quantum mechanics, right, because electrons and as well as protons to a large extent are quantum particles. So they have behaviors that are slightly different from how classical classical particles behave. I mean the famous example is the Schrodinger's cat, right. So this is the famous analogy that Schrodinger gave that if you have a cat in a box that is exposed to a slowly decaying poison, what is the probability that the cat will be dead or alive? Schrodinger said no, he actually truly does not know, the cat can be both dead and alive, right. So of course cat is still a classical particle, so it will be in one of the states, but the point is we do not know whether the cat will be dead or it will be alive unless we open the box. So we cannot predict that a priori, right. So electrons behave like that, so we cannot predict their states a priori very well, we can only get a probabilistic distribution of their states, right. So where an electron will be, how fast it is moving and so on, we can only give a probability to that, right. So since electrons are quantum particles, we have to worry about quantum mechanics, and the key equation in quantum mechanics is the Schrodinger's equation. This is the time independent version of the Schrodinger equation, which is a simple eigenvalue equation, right. So psi is your wave function, h is your Hamiltonian and E is your energy. So the Hamiltonian has various terms going into it representing different interactions, right. So that could be electron-electron interactions, that could be electron-nucleus interactions, nucleus-nucleus interactions and so on. And psi basically represents a many body wave function. So let us say you have n particles, right, so n electrons in your system, you would need a wave function that is representative of all the n electrons in your system, right. And each electron can locate itself in 3-dimensional space, right. So this psi can be quite a complicated function because it can have 3n dimensions, right. So each electron has 3 dimensions, you have n electrons, so you have 3n dimensions. But if you know the right wave function, basically you can pass that on to the Hamiltonian, right, and you can get back the energy associated with that state, right. And if you have several possible states in your system, you can get the energy of the ground state and also the excited states of your system, right. But in short, if your psi is known, you basically know everything that is necessary or needed to know about electrons in a given system, and once you know everything about the electrons in a given system, you can basically know everything about bonding in that system, and you can start predicting properties associated with that given system, right. So the key to everything is basically how accurately we can get an estimate of this wave function here. Okay. So if you unpack Schrodinger's equation a little bit, you would see that this equation, although it looks very trivial, it looked very trivial in the previous slide. It looked like a simple eigenvalue equation, right? But it's quite a complicated equation itself. So if we unpack it, the Hamiltonian itself can have 5 different terms. So the first term is basically your kinetic energy of electrons here. So this is basically the second derivative of your wave function, and these are units that normalize to give you kinetic energy, right. So think of them as half mv square, but slightly mathematically modified. So once you have kinetic energy of electrons, you can also have kinetic energy of nuclei. So just like electrons can move in a system, nuclei can also move in a system, and nuclei, as most of you know, is the collection of protons and neutrons, right, in a given system. So you also need to worry about kinetic energy of nuclei, right. And then electrons by themselves have the same charge, so they are both -1 atomic units of charge, and hence they will repel each other, right. So identical charges repel each other, opposite charges attract. This is basic electromagnetism, right. So you need to worry about how electrons repel each other, right. Second is nuclei, on the other hand, will attract electrons. So we should worry about nuclei electron attraction, and nuclei amongst themselves will repel each other, right. So we also need to worry about nuclei repulsion. You would also notice the signs associated with each of these energy terms here, right. So in general, if you think about nuclei electron attraction, it is associated with a negative sign. So if a nucleus and an electron approach each other, so their distance actually reduces, the level of attraction goes up, and the potential energy associated with that nucleus and an electron actually goes down, right. Whereas if 2 electrons actually come close to one another, then they start repelling more, and the potential energy actually goes up, right. So that's why you see the signs also, the corresponding signs associated with each of the Hamiltonian terms, right. So as you probably see, this is not a very trivial Hamiltonian to deal with. So we start off with the Schrodinger equation as one of our most fundamental equations, but the equation itself is fairly complicated, which implies we will probably need some additional approximations, right, to arrive at a more tractable form by after which we can solve the Schrodinger equation. So the very first principle that helps us make the Schrodinger equation more tractable to solve is what is referred to as the Born-Oppenheimer approximation. So very briefly, so if you think about the mass of nuclei with respect to mass of electrons, right, you would see that typically nuclei are several orders of magnitude heavier compared to that of electrons. So to give a simple order of magnitude sense, right, if I am not wrong, a proton is about 3 orders of magnitude heavier compared to that of electrons, and if you take a typical nucleus, you will have a few, at least a few numbers, if not tens of protons, as well as some amount of neutrons as well. So the electron masses are going to be very small, and the nuclei masses are going to be very large, maybe 3 to 4 orders of magnitude larger compared to that of electrons. So to sort of give a solar system kind of analogy, right, so this is similar to how the earth sort of rotates around the sun. So the sun is several orders of magnitude heavier than the earth, right. So the sun is also moving, it's not a stationary object, but the earth sort of moving around the sun is basically a very small, a tiny object moving around a very big object, right. So that analogy is how your atoms are. So electrons are tiny objects that are moving around, zipping around a given nucleus, which are heavy objects. So given this mass disparity, right, so given that nuclei are fairly large objects compared to that of electrons, we can sort of say that or it is sort of intuitive to think about that nuclei are generally much slower compared to that of electrons. So they don't move as quickly compared to that of electrons, and this once again comes from the solar system analogy, right. So if you think about models of solar systems, you would almost always treat your sun as a stationary object at the center of your solar system, and then all the planets are sort of rotating around it, right. It's not like the sun is not moving once again, but just that the relative motion of the planets around the sun is much more rapid compared to the motion of the sun itself, right. So we could treat the nuclei in our system as stationary objects, and the electrons to sort of go around the nuclei, right. So this can actually help us solve or make the Schrodinger equation a little less complicated, right. So what Born-Oppenheimer basically proposed was that so in our system both electrons and nuclei are moving, so we inevitably have to model both of their motions, but what we do is we decouple both of these motions. So we first say that we fix the nuclei and then we solve for where the electrons are actually moving, right. So we solve for the positions of the electrons, and once the electrons have moved and identified their sort of equilibrium kind of positions, then depending on the positions of electrons we then move the nuclei, right, because depending on how the electrons are sitting, you would now have a net maybe an attractive force or a repulsive force between different nuclei, which will dictate where the nuclei are going to move, right. So we are basically decoupling the motion of electrons from the motion of nuclei, right. So this was the approximation proposed by Born-Oppenheimer, and it sort of works very well for most of the systems, most of the practical systems of interest for us. So mathematically the way this has consequences is that, so initially you had this giant complicated Schrodinger equation, right. So where you had 5 different terms, you had kinetic energy of electrons, kinetic energy of nucleus, electron-electron repulsion, nucleus-electron attraction, and then nucleus-nucleus repulsion. So now we are decoupling the dynamics of your electrons and nucleus. So in just to give a clarification, so ions are normally nuclei, right. So in sort of quantum mechanics literature, nuclei and ions are words that are used interchangeably, okay. So what Born-Oppenheimer does is it separates out the electron and nuclear dynamics or ion dynamics. So when electrons are moving around, nuclei are considered to be stationary objects, so they are not moving around, which implies their kinetic energies are going to be 0. So this term sort of drops out, and since nuclei are now fixed, right, so their positions are now fixed, which implies nuclei repulsion is just a constant term here, right, and the attractive terms of nuclei with respect to electrons are only dependent on the positions of the electrons, right. So this can be sort of modeled or thought of as some kind of an external potential that is acting on the set of electrons that we are modeling, right. So because the nuclei are going to be in fixed positions, they can contribute a net electrostatic potential within which the electrons have to move, right. So these two terms can be modeled as some kind of an external potential, the kinetic energy drops out, and then you only have the kinetic energy of the electrons and the repulsion term associated with the electrons, right. So we now see that the electronic motion has been completely decoupled compared to that of the nuclear motion, right. So we first solve for the electronic motions, so we identify an appropriate wave function that can model all our electrons, so we do not have to model the nuclei here, so we only have to model the electrons here. So once we identify an approximate wave function, we can then calculate the energies associated with the electrons, right, given the position of nuclei. And once we know the position of electrons, we can then recalculate what are the forces that the nuclei are experiencing due to attraction between the coming from the electrons and also their own repulsions amongst themselves, and then we can model the motion of the nuclei, right. So the motion of the nuclei is usually done with what is referred to as classical dynamics or molecular dynamics. And the way this is done is typically using Newton's laws, right. So you have two sort of rigid spheres, nuclei, basically exerting a force on each other. The force is going to give the contribute some amount of acceleration, the acceleration is going to contribute some amount of velocity, and that velocity is going to contribute some amount of displacement in a given time interval, right. So for a given time interval you can sort of decide on how the nuclei are going to move, so and then you update the positions of the nuclei and then you sort of recalculate the positions of electrons around them. So the motion of nuclei it's decoupled, is modeled classically. The motion of electrons where on the other hand is still modeled using the Schrodinger equation, is still modeled quantum mechanically. Okay. So given this Born-Oppenheimer approximation, right, the Schrodinger equation that we saw before can be solved exactly for the hydrogen atom. So we have a one nucleus one electron system, and for this one electron system we can actually solve the Schrodinger equation exactly, right, and this exact solution is fairly well known. It's mathematically a little complicated, so we won't go into the details. But the basic procedure is that you take the overall wave function, you decompose or project the wave function into orthogonal basis sets, one set of bases that corresponds to radial functions, so the distance associated with the electrons away from the nucleus, and another with respect to angular terms, so where the electron is actually located with respect to an angle, right, so that can be along the plane of the nucleus, that can also be beyond the plane of the nucleus on the z axis here, right. So we sort of decompose our wave functions into radial as well as angular bases, and you can actually end up solving it, and you basically get representations of different orbitals, right. and we can also visualize these orbitals. So the first simplest orbital that the electrons can occupy is the s orbital, right, and the principal quantum number associated with that s orbital is 1s. So in a simple hydrogen atom, the 1s orbital is partially occupied, so there is one electron sitting in that 1s orbital. We can also think about other orbitals. So if you increase the quantum number to 2, then you can start getting p orbitals. So these look like nice dumbbells. When you increase the quantum number to 3, so basically make the orbital bigger, then you can get more complicated orbitals, the d orbitals here, and then increase the principal quantum number to 4, you can get f orbitals also. So these orbitals or the visualizations of these orbitals come from one of the basis functions we use, which is referred to as spherical harmonics, and it is these visualizations of orbitals that are still used to interpret the positions of electrons in modern day literature, right. So great, right. So we can use Born-Oppenheimer approximation, which was the very first principle, to solve the Schrodinger equation exactly, but that is about where we can go. Right. So if you start adding one more electron to your system, so if you take a simple example of a helium atom here, so one more electron to your system, you can no longer solve it analytically, right, and that is largely because of this electron-electron repulsion term, right. So this is sort of a E square by R2 minus R1 term, right. So R2 minus R1 basically refers to the relative distance between the two electrons, and as one electron updates its distance, the second electron will also update its distance, which will affect once again the distance of the first electron and so on, right. So if you think about this is a very sort of recursive problem. So whenever this electron is going to move, it is also going to affect the motion of this electron, and whenever this electron is going to move, it is also going to affect the motion of this electron. So since this has a sort of recursive cause and effect playing out, we simply cannot solve it analytically, but we can do it numerically, but for numerical solutions we need further simplifications. So the very first simplification that came up was what is referred to as the Hartree approach. So Hartree approach excuse me. So what Hartree approach does is it decomposes your multi electron wave function. So in the case of a helium atom, it's a 2 electron wave function into a product of single electron wave functions. So these single electron wave functions can in very simple terms can be just orbitals. So this could be 1s, this could be 2s, this could be 2p and so on, right. So it just decomposes a single wave function into a product of multiple 1 electron wave functions. The Hartree approach does not by itself include the spin as a variable of electrons. So if you are only modeling 1 electron in a system, then it does not matter whether that electron chooses an upspin or a downspin, because you can always change the direction of orientation of your spin to either call it up or down, right. So the direction is sort of irrelevant there. But when you have 2 electrons, then we need to worry about the direction of the spin as well for both the electrons. So recollect that electrons are quantum particles, so they have spin as an additional degree of freedom compared to classical particles, which do not have spin as an additional degree of freedom, right. So since you have spin as an additional variable, and if you have 2 electrons, you need to worry about which electron has the upspin and which electron has the downspin. So both are important, right. So if we were to include spin as an additional variable, then we have to generalize the Hartree approach, and the way to sort of mathematically do it is using what are referred to as Slater determinants. So we basically normalize these wave functions to build the variable of spin into it, and that approach is what is referred to as Hartree-Fock approach. We look at the Hartree-Fock approach in the very next slide, but both Hartree and Hartree-Fock approaches are computationally very expensive. So if n is the number of electrons in your system, they sort of scale as n to the power 5 to n to the power 7. So you see that even if you cross about 10 electrons or so in a given system, this computational approach is going to become increasingly untractable, right. So you are just not going to be able to solve those solve practical solid systems in any reasonable amount of time. So just to give an example, right, if you take sodium chloride or even sodium oxide for example, right. So sodium oxide will have Na2O, so there is 2 sodiums and then there is 1 oxygen. So oxygen has an atomic number of 8, so there are 8 electrons there, and then sodium has an atomic number of 11, so there are 11 electrons. So you have 2 sodium atoms, so that's 22 electrons, and then you have 1 oxygen, that is 8 electrons, so there are 30 electrons. So even modeling 30 electrons with this approach is going to be hugely complicated. So modeling one molecule of Na2O, forget the units, for modeling one molecule of Na2O is going to be extremely hard with this Hartree-Fock approach. But it is still a very important approximation, and to understand the importance of Hartree-Fock approach and the importance of spin, we need to also focus on the second principle, which is the Pauli's exclusion principle, right. So as I mentioned before, electrons are quantum particles, and since they have spin as a variable, the electronic wave functions are actually antisymmetric in nature, right. So what do I mean by antisymmetric in nature is, if you swap the positions of 2 electrons right in a given space, their energies may not change, but their wave function will actually swap, the wave function will change its sign, right. So we need to sort of introduce this antisymmetric nature of electrons within the wave functions that we define to model the electrons, and the way Hartree-Fock did it was using what are referred to as Slater determinants, right. So very simply what they did was, so you take this 1 electron wave function, you take this many body wave function, the way Hartree defined it was just a simple product of all the different 1 electron wave functions, right. The modification is basically you put in a determinant and sort of call in the 1 electron wave functions for different positions of the different electrons. So you basically define a determinant of these 1 electron wave functions instead of just defining a product of the wave functions. So this may look complicated, so if you generalize this for a simple 2 electron system, so for our helium atom here, so our 2 body wave function basically becomes chi1 chi2 minus chi1 chi2 here, but the positions are different. So this chi1 of x1 basically refers to electron 1 occupying position 1, this is electron 2 occupying position 2, and this is basically electron 1 occupying position 2 and electron 2 occupying position 1 here, right. So these are 2 electrons occupying their respective positions, these are electrons occupying their swapped positions, this is electron 1 going to electron 2 side and vice versa here, right. So the wave function is basically defined like this. Now if you actually swap out x1 and x2, so if you actually exchange the 2 electrons, you will see that the wave function will automatically change its sign. So it is equivalent to swapping 2 rows in a determinant. If you swap 2 rows in a determinant, that causes a change in sign of the determinant. And if you put together this 2 body wave function into the electron repulsion term here, right, which is the key term that prevents us from analytically solving a 2 electron system and so on, you get 2 separate terms that come out. So one is referred to as the Coulomb or Hartree term, which is the simple electrostatic repulsion that comes from the 2 electrons interacting. Other is what is referred to as exchange term. This is also an electron repulsion term, but it has a negative sign associated with it, right. So this basically takes into account the nature that electronic wave functions are antisymmetric by construction, right, or antisymmetric in nature, right. And typically this Coulomb or Hartree term is a positive term, so it increases the energy of your system. The exchange term is a negative term, it decreases the energy of the system, right. So using or building in Pauli's exclusion principle ensures that you introduce a new term in your Hamiltonian or your energy called the exchange term, right, and this exchange term normally results in lowering the total energy of our system. So if we are modeling electrons, or if you want to optimally find out the positions of electrons, first is we use Born-Oppenheimer approximation to make the math a little easier. Second is we have to use Pauli's exclusion principle to make sure that our electronic wave functions are antisymmetric by construction, right, because we cannot have symmetric wave functions because electrons are quantum particles, right. So with this we will sort of stop today's lecture or stop the discussions of DFT, and we will continue on in the next lecture. So just to give a recap, we sort of saw the importance of identifying the optimal positions of electrons resulting in bonding in a given system, and how bonding leads to several different properties of a given system. And for identifying optimal locations of electrons, we need to basically get a very good approximation of the many body wave function, that goes into the Schrodinger equation. So solving the Schrodinger equation as accurately as possible is the key. We sort of introduced two approximations that help us solve the Schrodinger equation to some extent. One is the Born-Oppenheimer approximation, second is the Pauli's exclusion principle. So in the next lecture we will touch upon the basics of DFT and then build from then onwards, right. So with that I thank you all for joining today's lecture. I will see you all in the next one.